And I'm not going to solve it in full detail, but I want to come to the point, okay, do we know or can we write down the random variable that we are dealing with or that we have to deal with in this problem? Yeah. So here comes the story. We have computer maintenance costs for a research unit at the Faculty of Economics and Business, and they are modeled as follows. We have the distribution of the number of maintenance calls each machine will need in a year, and that is Poisson with mean 3. So that means that the lambda parameter is equal to 3, and that is capturing the number of maintenance calls per machine in a year, let's say. The cost for a maintenance call has a certain mean and a certain standard deviation, and the number of maintenance calls and the costs of the maintenance calls, they are mutually independent. And we're going to consider all the computers to be mutually independent. Now, you could question that assumption, but for now, that's okay. So what do we need to solve? Well, the department must buy a maintenance contract to cover repairs if there is at least a 10% probability that aggregate maintenance costs in a given year will exceed 120% of the expected costs. So can you then calculate the minimum number of computers, which is necessary to avoid having to buy this maintenance contract? Yeah. So I think what I want to think about together with you, without solving the question at this point in full detail, but what I want to think about with you is how would you describe the total maintenance costs in a given year, and how would you work with the mean and the variance of this total aggregate maintenance costs? Yeah, I think that's what I will try to solve with you. Okay, so let's take a moment to think about that. So we have in bullet number 1, we have the distribution of the number of maintenance calls per machine. So what I'm going to do is I'm going to write that as Fi, say. So F for frequency, for number of calls, and that is for machine I. And this is a Poisson with lambda equal to 3, right? So that's the number of calls that each machine I is going to make, right? We're going to wonder about what's the total number of machines that we need to fulfill a certain condition. So we're going to work with a certain I that is running from 1 up to n. And this n, the number of machines, that's something we need to solve under a given condition. Yeah. So that's my small n. And then I know something about the cost for a maintenance call. So the cost for a maintenance call, I'm going to denote that with, say, xij if you want. So I is the machine, j is the jth call that I have to make on this machine. And this is following a certain distribution with a certain mean. I'll say xij is 80 and a certain standard deviation, say 200. Yeah, but there is not much, there's no additional information. We only know these something about the mean and the standard deviation. Yeah. Then we're going to think about what would be the aggregate maintenance cost. So the aggregate maintenance cost, if you work across all these machines in the department. So we need to worry, or we need to think about what will be the aggregate maintenance costs in a given year. And this, so the department is required to buy the maintenance contract if, with a probability of 10%, these aggregate maintenance costs exceed 120% of the expected cost. So the expected cost, that's something we can calculate if we write down the aggregate maintenance costs in the appropriate way. Yeah, so that's what we're going to do. Any questions at this point? All right. So how would you write this it over here. So how would you write these aggregate maintenance costs? That's the next question. And this has to go across all the machines. So the aggregate maintenance costs, that will become a sum over all machines in the department. And then per machine, the maintenance costs over a year will be written with a sum once again. And per machine, we are going to sum over the random number of calls that one has to make for this machine I. And we're going to sum the costs of the interventions that we have to make for this machine I, right? So this is a sum over all machines in the department. And this is then the cost, or the total cost, I would say, or the total loss for machine I. And then for machine I, you know, of course, that the number of interventions will be random. That's captured by this Fi. And then, of course, the sum of each intervention is a random variable again. That's this Xij. All right. Now, what can we say about the expected value of this aggregate maintenance cost? And what can we say about its variance? So this is my S, and I'm going to work with this S. Think about the expected cost, for example, in a first step. Yeah. So what can we do now? We can look at the expected value of S. We have these independence assumptions, so of course we're going to rely on that. So that means we can do n times the expected value of one of those guys, because I have these, shouldn't stress the independence assumption, but because I have these identical distributions for the number of interventions and for the cost of each intervention across all the machines in my portfolio. And then, of course, if you look at the expected value of the compound sum, then you know what we learned in class. So you're going to use, if S is, let me put that differently. So you're going to use the expected value of a compound sum, and under independence assumptions between the frequency of the events and the severity of the events, you can write this as follows, right? And we're going to assume not only independence, but we're going to assume identical distributions. So we can write this as n times the expected frequency times the expected cost of a single intervention. Now we know something about this F. This F is Poisson, with a parameter lambda is 3, and we know something about the X, so the severity, because we know what the expected value of X is, and we know what the standard deviation of X is. And you can find that in the bullets which are given in this question, right? So you get something like this. Now, what about the variance of S? Let's think about that one as well. So when you're dealing with the variance of S, you're going to look at the variance of the sum over I and then the sum over J, like this. You're going to use the independence assumptions, which are given. You're going to use the fact that distributions are identical across machines. So what we get is n times. And then I need the expression for the variance of a compound sum. Right? And this is something we learned. So how would you express the variance of this compound sum? I think we did that earlier on last week. So that would become n times the expected value of F times the variance of x plus the variance of f times the expected value of x squared. And now, of course, there is something funny over here, which allows you to simplify this expression one step further. What would you use then? Could anybody in the chat perhaps indicate which extra step I could use to further simplify the last expression? Any ideas there? What do you know about this distribution of f? Yeah, very good. Milou and Sebastian. So in this particular case, because f is a Poisson, the expected value is equal to the variance. So we can write this eventually as n times lambda times the variance of x plus the expected value of x squared. And then, of course, in the last step, I can further simplify this by saying, okay, that's the expected value of x squared. Yeah. So then you have your ingredients for the distribution of s, in the sense that you know its expected value, you know its variance. So you can use, for example, a normal approximation, because that's what was requested in the exercise, that you then try to solve a certain condition using a normal approximation for this s. And then, of course, you have to match the moments of s with the moments of your normal approximation. All right, any questions? So I particularly wanted to, to demonstrate how we can bring this whole story, how we can bring it down to the appropriate random variable, in this case, the total loss s across all the interventions, how you can write it down like this and then start working with it. So Feng is asking, thank you, Feng, how is the variance of x, how is that gone in the last step? Yeah, so what I'm using here is the fact that the variance of x in shortcut notation, you can write it like this. And then, of course, we see that here we have the variance of x plus the first moment squared. So that's exactly what you get over here. That's following like this. Does that help? Okay, good. So don't hesitate to launch a question, small things, bigger things. That's why I'm live teaching, because I would like to show you that I'm here to try to do my best to help you with these exercises and this material. All right, good. So that being said, we're going to continue with our book, with our content over here. And yeah, so I have one more question from Sebastian. So let's solve it, or let's answer it as well. So how would you then move on to get the value for the second moment of x, because there is no distribution specified for x? Well, you've got the standard deviation of x, and you've got the mean of x, so you can directly calculate this sum, right? Because you've got the standard deviation, so you square that to get the variance of x, and you then add the square root of the first moment of x, the mean of x, which is also given. Yeah? So you've got all the ingredients that you need in order to actually put a number on this. Of course, the unknown here is the number of machines that the department should get, but that is what the whole question is about, right? Determining this number of machines. And I agree, Sebastian. Yeah, so I didn't need this step, but I just wanted to show you. If you see something like this, variance of x plus the mean squared, then you immediately think about, okay, that's the same as the second moment of x.